Welcome to CERIAS Security Seminar. I'm Ninghui Li. I'm actually the official instructor for this course. I'm a professor of computer science here at Purdue. I joined Purdue for now, I guess, close to 12 years, more than 11 and a half. And my research are in security and privacy. Yesterday, I was reminded that the speaker that's originally scheduled for today canceled. I probably got the notification earlier, but I didn't pay attention, so I received the reminder yesterday. So I guess one of the perks of being the instructor of this course is I get to give this talk today. I'm going to talk about privacy in data publishing and analysis. And this is an area that my research group has been working on for, I guess, about 7-8 years now. We all know we live in an information age, and the fuel for the information age is data. So we are generating a lot of data, and those data can be very useful as well. So it's often one entity or one organization collects the data, and then it's necessary for them to share the data with other entities so that the data can be better used. So there are different reasons for such data sharing. One obvious one is for research. So researchers want to analyze, for example, medical data, genomic data, in order to discover better treatment and to figure out what works and what does not. And some of the sharing are mandated by law and regulation. For example, the US Census Bureau does a census every 10 years, and they collect a huge amount of data. And they, by law, they have to share that data in some form with the public. And the social scientists and policy makers, they will analyze those data to identify what needs to be done to improve the social, social justice or social benefit. And of course, there's also data are needed for decision making, either in business or in security purposes. For example, it would be really nice if we can monitor internet traffic at different points and then correlate the information so that to decide whether there's some kind of attack going on. But in all of this kind of sharing situation, one critical consideration is privacy. Oftentimes, the way the data is collected, the data is about some individuals, and those individuals do not want their data to be shared with the public. So we want to use this data in a way that preserves the privacy, at the same time be able to learn useful information from the data to benefit the public. So one of the main areas that researchers are working on is to try to define this privacy precisely. So we want to know what exactly is privacy are we talking about. And in the tradition of security, oftentimes it's very hard to define what is security, but it's somewhat easier to define what is insecurity, when something is bad. But if we can precisely define what is bad, then we have a definition for what is good. So security basically means none of the bad things happen when we are under attack. So similarly, we apply the same method for defining privacy. We want to define what is a privacy violation. And then privacy simply means privacy violation does not occur. But privacy is not just a technical concept. I can't really just just looking at the problem only from a technical point of view doesn't make sense, because privacy is about individuals and it's very much a social concept. So in order to define what is a privacy violation, we have to look at the social societal responses to different things and infer what the society consider as privacy violations. And then we can try to distill what are the essence of privacy violation in those scenarios. So therefore, we're going to look at a few situations where I think the public in general agree a privacy violation occurred, and it has significant consequences, both for the research community and for the general public. So the first example is documented by Latanya Sweeney when she was a PhD student at MIT. The organization Group Insurance Commission operates the health insurance for all the public employees of the state of Massachusetts. And so they collect all this medical data about public employees of Massachusetts state. And then they give this data to researchers, and also they actually also sell this data to the industry. But of course, they know they can't share this data in the form that they get them, because that would be obviously privacy violation. So what they did is they tried to anonymize the data, so remove the name and other obvious identifiers, which would include, I imagine, phone number, social security number, address, because those things can be easily linked to individual identities. However, what remains in the data are date of birth, gender, and zip code. And what Latanya Sweeney found is that using these three pieces of information, over 80% of the population in US can be uniquely identified. And in fact, and also you can get this data from other sources. So in fact, the voter registration list include all this data, and you can buy voter registration list from some government agency. I think, I remember for $20 you get the voter registration list, and then you correlate that with here, you can find all the medical record of all kinds of individuals. In the paper, she mentioned that she can find the medical record of the former governor of Massachusetts, and obviously many other people can be found. So this was considered a privacy violation. So I think everyone agrees. Now, at the abstract level, why this is a privacy violation? I believe that what happened is the data is supposedly to be anonymous, because when the health insurance company collects our data, they don't have the right to give our data to the public. However, the reason they gave it is because they assume it's anonymous. But in this case, we can re-identify the supposedly anonymous record. So we can point to a record and say, I know this record belongs with this individual. And because of this re-identification happens, there is a privacy violation. So then this work sort of jump-started the last, I guess, 15 years or so, intensive research in the research community to try to study data privacy. So there were a lot of research before that, mostly in the statistical community. They figure out how to publish statistical data about the data set while preserving individual privacy. But this work sort of made attract the attention of the computer science community to look at this problem intensively. So the second example I want to talk about is this American Online data release. So I don't know, any of you remember this incident? Yeah, some of you do. So in 2006, AOL released the search keywords of, I guess, over 500,000 users over a 3-month period. So obviously, user IDs need to be anonymized. They are replaced by random numbers. So in a sense, this is a good thing. So as a researcher, one of the sort of most valuable things is real data. So the fact that AOL is releasing the data is really to the advantage of the research community. Something from a researcher point of view we should really encourage. Unfortunately, the anonymization method they did, which is just replacing the IDs with random numbers, is not good enough. And I think they might have also done some other things. Because if you think about it, think about your own search record. Identifier doesn't really matter. So I think myself, I search my own name, if only to find the DBLP page of my publications to get information from it. And also I search my own address a lot, because I want either for driving direction or search for a restaurant near my address. So the search record actually is easily linked with the personal identity. So I think AOL probably did something to remove those obvious links, but that's not good enough. So 3 days later, an article appeared in New York Times. 2 reporters showed that it is possible to look at this supposedly anonymous search record and then re-identify individual. And in particular, the article, I think the article is titled "The Face is Shown." So the face that's shown is this lady. And if you look at the search keyword, it includes the town name that the lady lives in. So that narrows it down. And it includes a lot of query with a last name Arnold. So the reporter inferred that the lady's last name must be Arnold. So then they basically look up the white pages, the phone directory, to see, they find, I think, maybe a dozen or so entries with the last name in this town, and they call them one up, one by one, and they confirmed, this lady confirmed that this record is hers. So, and I guess also think about, what are the sensitive information that might be included in your search record. So at least personally, I think the things I search, I consider is really sensitive. At least there are really sensitive things included in my own search record. I definitely don't want people to know what are the things that I'm searching. So this is a second example. And in this case, there's a serious consequences. So AOL pulled the data immediately after New York Times published the article. But of course, as we all know, in the internet, once the data is up there, it's always out there. You can't really retract it. So in fact, you can download the AOL search dataset today from the internet. And in fact, I think many researchers actually use the dataset, but mostly for other researchers, mostly just use for example, keyword. For example, for frequent item set mining kind of research instead of trying to learn sensitive information. And also the person directly in charge was fired. I think some executive was fired. And as we are in America, there's a class action lawsuit followed. And AOL, I think, settled out of court for a multi-million-dollar fine or settlement. So again, in this case, I think it's a privacy violation because the data is supposed to be anonymous. Because if it's not anonymous, AOL shouldn't share the data. But while it's supposed to be anonymous, we can do re-identification. So then this is a privacy violation. So the last example I want to talk about is in this Genome-Wide association study known as the GWAS study. So a typical study will examine many individuals in two different groups. One group are individuals that have certain disease. A control group are individuals that do not have the disease. And the researcher will look at the genomes of the two groups and try to find out which genes or genomic information, DNA information, is highly correlated with the disease. And therefore, we try to understand what causes the disease and try to find treatment. So there are lots of this study going on. And a typical study will examine many of these locations on the genome where people differ, because for a vast majority of the location, everyone are the same. But for some of the locations, the genome differ, and they differ in sort of in a significant sense. I guess this will result in different protein being expressed from the different genome. And as a tradition, when you do this research, you want to make the data sort of available so that other researchers can do similar analysis to validate your research. So the norm is people will publish aggregated statistics, basically the frequency of the different variants on a particular location in the disease group and in the control group. So this is sort of the form of the data that is published. We will look at many different locations on the genome. So these are known as SNPs. So for each of the location, we will publish, and for each of the location, typically there are two variants, variant A and variant B. So some people have variant A, some people have variant B. So they will publish aggregate of each of the groups. So for example, here we are seeing for the disease group on SNP1, 43% of people have variant A, meaning 57% will have variant B, and so on. So they also publish this for the control group, but the control group is not important for the particular attack. So this was what people have been doing for years. And then in 2008, a group of researchers published an article showing that there's actually privacy implications in publishing this data. So the assumption is that the attacker will know the average of the population where this disease group is drawn from. And in addition, if the attacker also knows one target individual's genome information, then the attacker can infer whether the target individual is in the disease group or not, even though this group are aggregate of potentially hundreds of individuals. So the intuition is that suppose we know the population average for SNP1 is 42%. So, and we know that the target individual has variant A. Then we would expect, on average, the disease group average to be slightly higher than the population average, because the target individual contributed to this variant A percentage. On the other hand, if the target individual does not have does not have variant A, for example, for SNP-B, we would expect that the disease group average to be slightly lower than the population average, because the target individual, if the target individual is part of the disease group, we would expect that the disease group average is slightly lower than the population, because he sort of contribute to the other case. So every single SNP provides a very noisy signal of whether the individual is in the group or not. So if you just have a few of these signals, it's not enough for you to conclude that whether the individual is in the group or not, because any difference between the disease group and the population average could be explained by random noise. However, when you have tens of thousands of such noisy signal, then the aggregate signal becomes very strong. So you can conclude the person is in the group or not in the group with very high confidence. So that's what this paper showed. And this also had significant impact. So the National Institute of Health changed their regulations about how you should publish this kind of research data. So now this aggregate data is no longer made publicly available. So it's collected in some database, and if you want to access it, you have to have an account. You have to basically kind of certify some process that you are a researcher in order to get the data. And similar policy change was adopted in UK by similar funding, the corresponding funding agency. So again, in this case, the public believe there is a privacy violation. But here, we have something that's somewhat different from the previous two cases. Here, there's no re-identification. There's nothing that we point to something and say, this record belongs to this individual, because the data we have is actually aggregate information. So what I believe what happened here is something called the membership disclosure. So looking at the data and knowing one individual's information, I can say with high confidence the individual's data contributed to this input. So I know the individual is a member of the data set that generated this output. So apparently when this membership disclosure occurs, the public agree there's a privacy violation. So then I want to point out that suppose we can eliminate membership disclosure. Suppose we make it impossible for you to conclude that this individual contribute to the public to the data that generated the output. Then we also eliminate re-identification, because if you don't even know the individual is in the input, you can't possibly re-identify by saying this record belongs to this individual. So re-identification implies membership. From the other way, if we can prevent the membership disclosure, we prevent the re-identification disclosure. So that's sort of the intuition that led to the later privacy frameworks that we developed called membership privacy. Basically, we are trying to prevent people from learning membership information. So I mentioned that I've been working in this area for a number of years, and in our research program, there are basically two main goals. First is to come up with the right definition for privacy, and the second is once we have a definition, we want to be able to either publish the data or anonymize the data so that we can satisfy the privacy requirement. At the same time, we want to be able to learn useful information from the data. Because if the only thing we want is privacy, then it's easy, right? We just don't publish the data. So the reason we want publishing data is we want to get some utility of the data. So it's the trade-off between privacy and utility that makes this challenging. So I've given sort of motivation for the work, and next I will talk about the evolution of privacy notions, I guess, in the computer science community over the last, I guess, 15 years or so. And then I'll talk about the current sort of standard privacy notion, which is differential privacy, and our work membership privacy, which sort of generalize differential privacy. And if we have time, I'll give some example about privacy preserving data publishing. If not, then I'll just skip that part. So if any of you have questions, you can just raise your hand, interrupt me. Okay, so so Latanya Sweeney discovered this this attack in the Massachusetts healthcare data. So she also proposed the privacy notion together with Pranjula Samarati. They proposed the concept of k-anonymity. So the intuition is you don't publish precise data. You make the data sort of you do what's known as generalization. You make the data less precise so that if the attacker knows some information about the individual, then knowing this information, he cannot pinpoint one record and say this record must be this individual's record. So whenever they find a match, there must exist at least a K record that matches this information. So the attacker would know one of the K records correspond with the individual, but he doesn't know which one. So that's the idea of k-anonymity. So this notion relies on a set of attributes you assume the attacker already knows, and these are known as a quasi-identifier attribute, QID. And then you assume the rest of the attribute the attacker does not know, which are called here sensitive attribute. So in this case, you may assume the attacker knows zip code, age, or birthday, or gender, but does not know the disease information. So that's the intuition of k-anonymity. So this notion was proposed, and then people started working on how do we publish data that satisfy k-anonymity in a way that require minimum perturbation of the data. But then researchers started to realize, well, maybe k-anonymity is not good enough. So one attack is the sensitive attribute may lack diversity. So for example, in this case, the table that we publish is 3 anonymous, so it satisfies 3 anonymity. And suppose we know information about Bob, and then we're able to know, to tell that Bob's record is one of the 3, but we don't know which one. However, if all 3 records have the same value in a sensitive attribute, then we know that Bob has heart disease. So that seems something that's sensitive that can be learned from the published data. And similarly, this kind of attack can occur when the attacker already has some other background information. So for example, maybe the attacker knows Carl does not have heart disease. So this may be because of personal information, or maybe because whatever culture background or whatever thing you know, so that you know people like Carl are very unlikely to have that kind of disease. So given that background knowledge, then if you are able to match Carl to this group, then you know he doesn't have heart disease, he must have cancer. So then, because of these kind of concerns, this notion of L diversity was introduced, which requires that each of these equivalence class, so this record that have the same quasi-identifier values, they must have certain diversity in their distribution of sensitive attribute values. And there are sort of different ways of defining that. And then, so in a paper that our group wrote in 2007, we point out that even having high diversity, which basically means high entropy, is not good enough. Because sometimes the highest entropy may not be the most privacy friendly. So what kind of distribution we would want would depend on the distribution of the sensitive attribute value in the population. So the example we use in the paper is consider an attribute about the test of HIV status, so whether it's positive or negative. Well, if someone belongs to a group with maximum entropy, that means that half of the group is positive, half is negative. So the fact that someone belongs to that group may enable actually quite sensitive inference, because the background population may have a very low percentage of population that are tested positive. So basically, you have to look at what's the distribution of the whole data set. So we introduced this notion called the T-closeness, which require sensitive attribute value. The distribution of sensitive attribute value in every equivalent class is sort of closer to either the whole data set or a data set that's large enough so that whatever you can learn is not really individual, but rather sort of you are learning information about the large group. And along this direction, there are many other privacy notions. So some people call this sort of alphabet soup of privacy notions. So I guess we probably don't have 26 of them, but I think more than 10 you can find in the literature. Oftentimes, one paper proposes a notion, and next paper say, hey, see, this is not good enough. Now try this variant. So in a sense, the fact that people can sort of keep challenging each other about what is the right privacy notion suggests that there's something fundamentally wrong or not good enough with this line of work. So I think the main there are a number of limitations of the previous privacy notion. So including the notion proposed by myself. One of the problem is they all require you to identify which attribute the attacker you can assume they already know, quasi-identifier, and which attribute you assume the attacker do not know. So this is actually very hard. For example, if you think about census data, there are many attributes, and you're not defending against a single attacker. So you are defending against anyone who may be trying to learn sensitive information from the data. Some people may know some information about some individual, and other people may know different information about the same individual. So you can't really identify which are quasi-identifier and which are sensitive. And also, even if you say my quasi-identifier include every attribute, which seems sort of the maximum privacy that you would ever want to provide, that's actually not good enough, because all these privacy notions are syntactic in nature, meaning that the privacy is defined as some syntactic property of the output of the data set. So if you want to know whether a data set is private or not, you just look at the output. You don't look at the input. You don't consider the relationship between input and output. So one example that sort of illustrates the weakness of this is there's a trivial way of satisfying k-anonymity. That is, I take every record, I duplicate k time, and then I publish that as output. So it satisfies k-anonymity, but I'm actually not doing anything to the data. So I'm leaking all the information. Well, you might say no one is actually doing that, but in fact, some of the k-anonymization algorithms are doing things that's somewhat similar to that. So those algorithms will be grouping a bunch of records together, and then select one of the record in each group, and then duplicate that record k times as the representation of that group. So in a sense, we are not compromising the privacy of everyone, but we are sample some individual and then say, well, you guys are sacrificed. I publish your data unchanged. So as we have seen from the past examples, compromising the privacy of a single individual can have serious consequences in the AOL data case. So basically, privacy have this very much individual nature. So you have to protect the privacy of every single individual. So if you consider over all individuals, you have to provide the worst case protection instead of average case protection, saying on average people's privacy is protected, but then some people's privacy may be totally compromised. So that's not acceptable for privacy. So there's this limitation in that these privacy notions are purely syntactic. So I would like to make an analogy. This is like we are trying to define security of encryption, and we make the definition only depends on the property of the ciphertext. So we say, well, encryption is secure if the ciphertext contains the same number of zeros as the same number of ones, blah, 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 blah. That's never going to work, because any definition about security of encryption has to look at the transformation procedure. It has to look at what plaintext result in this ciphertext. If two plaintexts are always resulting in different ciphertext, then looking at the ciphertext, you can tell. If plaintext always result in different ciphertext, then looking at the ciphertext, you can learn what is the plaintext. So basically, the privacy notion has to be about the transformation procedure, and that's what this notion, differential privacy, which was developed mostly in the theoretical computer science community since around 2002, 2003. And eventually, they arrive at this notion called differential privacy, which is actually very elegant. So the intuition of this privacy notion is, suppose I have a data, and your data is is one of the records, and I want to publish the data. and you complain that your privacy may be compromised, then there's an easy fix for that, right? So I can throw out your data and publish the rest. Then you shouldn't be complaining that your privacy is violated if I'm publishing other people's data. But of course, we can't quite do that because you may complain about privacy, other people may complain about privacy, so then we have to remove everyone's data. So what differential privacy says is we can't quite achieve the goal that what I'm publishing is exactly the same as if removing your data. However, what we can do is what I'm publishing is quite close to what I might have published after removing your data. So even if I take out your data, there's some probability that I'm going to publish exactly this output that I'm publishing now. If I can do that, then I can say you shouldn't complain too much about the privacy because even if your data is not here, I'm still likely to publish this information. So that's the intuition of differential privacy. Another way to say it is whatever we are outputting will not be overly influenced by a single record. Will not be overly influenced by a single individual's information. So more formally, differential privacy is a notion about an algorithm. And because of the nature of the definition, the algorithm has to be randomized. So there's no way for you to have a deterministic algorithm of publishing data while satisfying differential privacy. And this algorithm satisfies differential privacy if for any pair of data sets that we call neighboring data set. And neighboring typically means that if I remove one tuple, I get the other data set. Or another variant is I change one tuple, I get the other data set. So both of these have been used in the literature. But the intuition is I change one individual's information, and then the output should be similar. And the similar is defined by this line of formula at the end, last line of the slide. What it's saying is, if you look at a set of possible output, so this defines output event. So for dataset D, the algorithm will have some probability of generating a dataset that's in this subset. So a particular output event may occur. For dataset D prime, there's also a probability that the same event may occur. Now, what we want is the ratio of the two probability is bounded by this parameter e to the epsilon. So when epsilon is 0, we are basically saying we are always publishing the same information on D and on D prime. But that will be too strong to require. So oftentimes, epsilon will be some small parameter. It could be 0.1, could be 1. So actually, how to choose epsilon is actually also sort of interesting and challenging problem that actually motivated Professor Clifton's, one of his written paper, not so written, I think 2-3 years ago, sort of motivated by the fact that it's unclear what epsilon means in differential privacy and try to have a way of assigning semantics to it. So that's sort of the definition of differential privacy. So any question about that? Yes?
How can you be certain that when you've applied this algorithm and you've got this data set output that it's going to be useful for researchers who are trying to ascertain something from that data set, if it's been kind of uniform, if it's made uniform?
A very good question. So I guess in a short answer is you cannot. But also, oftentimes when you publish the data, you have to have in mind some kind of query you still want to be able to answer correctly, or at least as accurately as possible. Because of the random noise, the perturbation introduced in the process, there are some queries are guaranteed to be not answered correctly. So the hope is that ahead of the time, we will know there are certain queries that are of interest and the other queries are not of interest to us. So then we preserve answer to those queries to be as accurate as possible. And that's sort of, in a sense, that's why sort of it's not, once we have the definition, we are done. It's when there are different data, when there are different tasks we want to learn from data, then there are different tricks you can use to ensure that you can get the most accurate or as accurate answer as possible while satisfying the privacy notion. So then people can keep improving finding out new algorithm to achieve better utility under the same privacy requirement. Any other question? So differential privacy is sort of very much motivated by the definition of secure encryption in the sort of cryptography field, because in encryption we are also saying, given to plain text, the output, you shouldn't really tell whether the output is this guy or this guy. So that's very similar. Yeah, so they're sort of, the differences are somewhat subtle, and it has a number of very nice properties, so that people really like it. So that's why this is sort of the in a sense the golden privacy definition today. One of them is the composability. So this means that if one algorithm satisfies differential privacy for epsilon 1, and another algorithm also satisfies differential privacy for epsilon 2, and you apply both algorithms on the same data set, the combined output will still satisfy differential privacy, but the parameter is epsilon 1 plus epsilon 2, because you have leaked more information by publishing both. But at least it's not catastrophic, so it's just a sort of additive. Gradually, the privacy decreases while you publish more and more. So this is a very important property. And also some sort of general facts is counting queries can usually be answered accurately because when you are counting how many records satisfy a particular condition, then changing one record can affect the result at most by 1. So therefore, you don't need to add too much noise to make to give a reasonable, accurate answer for a small number of counting queries. But some queries are very hard to answer. So one example would be queries like max, because changing one tuple can totally change the possible answer. So there's really, in a sense, no way to satisfy differential privacy while still give a reasonable answer to queries like that. And yeah, the main challenge in using differential privacy for a particular task is there are usually different ways of asking query so you have a final objective. So you typically translate that objective into a sequence of query. You ask the data, and then you combine the output in some way to give an answer. So depending on how you ask the query and how you combine the answer, sometimes you can get much better answer than some of the not as optimized methods. So that's sort of where the sort of the challenge is in sort of applying differential privacy in data publishing. And one thing that people often complain is satisfying differential privacy is actually very hard. And oftentimes practitioners, for example, if you talk with people in bioinformatics or analyze genomic data, differential privacy is sort of a non-starter, because people say, well, it's just too noisy. I can't tolerate that much of noise. So then, in a sense, there's it's not clear that differential privacy is sort of the answer to the definition of privacy. So maybe we can do with a privacy notion that is weaker, or maybe in some situations differential privacy by itself is still not strong enough. So we explore the situation that probably we can relax differential privacy. So the intuition is what differential privacy says is, suppose I have the attacker knows the input data is either a data set D or the data set with D with additional tuple T included. So the attacker knows everything about the rest of the data set. The only thing the attacker does not know is whether the particular individual's data T is in the data set or not. So differential privacy guarantees that the attacker's ability to infer whether T is in the data set or not, or in other words, whether the input is D or D union T is limited. So that's what differential privacy provides. But in reality, there's no reason for us to assume the attacker knows everything else about the data set, because that just doesn't make sense. So it seems that what we want to, it will suffice if we can protect the privacy so that the attacker knows one tuple, and then the attacker has statistical knowledge about the rest of the data set. In that situation, the attacker cannot differentiate between whether the input is D or the input is D with T added to it. So we are sort of the definition in this definition, D will be sort of a random variable that can be where the attacker have some belief about its distribution, but it doesn't know exactly which one it is. And we want to point out that in all the privacy incidents that we have examined, for example, the Massachusetts one and the AOL one, actually in both cases, the attacker does not need to know any statistical knowledge. All the attacker needs to know is one individual's information. Then the attacker can do re-identification. So this certainly protects against that. Even in the GWAS case, the attacker knows one individual's information and the sort of the general statistical information of the population. So again, that also falls under the protection of this notion. So we introduced this, but unfortunately, this privacy notion suffers from a very important limitation. That is, it's not composable. So if you publish, if one algorithm satisfies this and another algorithm also satisfies this, when you use them both and publish the result together can totally violate privacy. So this is sort of, I guess, very sort of, I wouldn't say heartbreaking, but it's sort of we come up with this notion that I think really makes sense, but in the end, it had this serious limitation. So I can actually give the intuition. So the intuition is, suppose there's one piece of sensitive information, and then suppose I publish something else that the attacker, I have another piece of information that the attacker, that is not sensitive. So one example is, let's say, the how many male tuple is in the if we're talking about the person's data, how many tuples are male. So when we assume the attacker is uncertain about background knowledge, then that piece of information is not it's okay to publish that piece of information. Now, if one algorithm publishes that information, the other algorithm publishes that information XORed with my sensitive information, then both algorithm individually will be private. So it's like publishing key is okay, publishing key encrypted message is okay, but when I publish both, then the message is revealed. So that's sort of the fundamental problem with this approach. And at the same time, there's a series of papers challenging differential privacy. So sort of coming up with different reasons. One paper realized that differential privacy is not as strong as people think they are. So people have made claim that differential privacy is robust to arbitrary adversary knowledge. So no matter what adversary already know, differential privacy will protect you. And it has this author argued that's not the case. And also, I mentioned earlier, Professor Clifton and his student argue that it's difficult to choose epsilon. And also, researchers argue that differential privacy does not prevent attribute disclosure. So even if the data is differentially private, suppose you provide good utility, then you can still learn good, let's say, classifier from the data, and then apply that classifier to individual, and now you learn more about this individual. So, so people have criticized differential privacy for that. But for this last point, I would argue that shouldn't be a privacy concern, because people could learn information about me without using my data. So let's say if people learn information about, let's say, Chinese who work in US university as a computer science faculty member, that information may very well apply to me, at least probabilistically. But I shouldn't complain my privacy is compromised because the information is learned without my data. So I can't possibly say no one can learn any knowledge that may be applicable to me. That would be absurd. So I would say the last one does not apply. But the point that people can criticize differential privacy, I think it means that there's room for examining whether differential privacy is really the end answer. And my belief is no, because actually it's somewhat a little bit, the differential privacy definition can be argued to be a little bit sort of unnatural. So sure, the intuition that if I'm publishing exactly the same thing, whether your data is in there or not, that's private. So there's no question about that. But the problem is differential privacy does not achieve that. It will publish things that are different, whether you are in there or not. But the difference is bounded by that epsilon. But what exactly does that mean? So, so we come up with a privacy framework that we call membership privacy by exploiting the notion, the intuition that we get from examining privacy incidents. We define privacy as basically positive membership disclosure. So if looking at what you publish, I can positively identify, say, now I know this guy is in the input, then privacy is violated. If I cannot, then privacy cannot. Then privacy is protected. But to formalize that is actually a little bit challenging. So we need to assume that the adversary has some prior belief about what the input data set will be. So this is modeled as a probability distribution over all possible data sets. And then after the adversary see the output, the adversary basically apply Bayes' rule to update his belief about, after seeing this, he knows this data set it couldn't be, and this data set now become more likely. So then the adversary can update his belief about the membership of a particular individual. And the requirement is for any tuple, the belief about this person's positive membership should not increase too much. So that's the intuition. But we don't know exactly what the attacker believes ahead of time. So therefore, the definition is relative to a family of prior distributions. So the attacker's belief, if the attacker's belief is taken from this family of distributions, then we can protect. We can ensure that membership inference does not, the confidence does not increase too much. So I will skip the formal definition here because it takes quite a bit of time to explain. So what we showed is that if you define privacy as we want membership privacy against the family of all possible distributions, so the strongest possible, that's basically infeasible. That basically says don't publish anything. Or you get an empty data set, what you publish with this data set should not be too different if you replace that data set with a completely different data set. If you achieve that, you achieve this membership privacy against the family of all possible distributions. So in a sense, you have to make some assumption about the attacker, even if you are using differential privacy. And in fact, differential privacy is equivalent to the membership privacy under the family of all distributions where membership of each tuples are mutually independent. So basically, differential privacy says if whether one guy's data is in the data or not is independent from any of the other guys in the data or not, then satisfying differential privacy means that you also protect membership privacy. So that there's basically equivalent. So you can, I guess, roughly see that from the definition because differential privacy said if you change one tuple, the output should be similar. But maybe whenever a change occurs, it's always multiple tuples. So for example, whenever my data is, if we are talking about medical data, maybe whenever my data is there, my family data are also there. So if you're only achieving differential privacy when changing one record, you're not really protecting my membership because even if I'm not there, my family member data there may influence the outcome, and you can learn information from that about me. So differential privacy is still limited. And then we show that all the other privacy notions that people have examined are sort of special cases of membership privacy. And we also come up with sort of the weakest privacy notion that you can have, which is membership privacy under the prior distribution where the attacker has a single uniform distribution. So the attacker believes any tuple in the universe could be in the input data set with some probability. And we show that, well, if that is your prior belief, then it's actually possible to publish information about the max with fairly high accuracy. So basically what we are saying is if you allow a weaker privacy notion, which maybe not good enough for some cases, but good enough for others, then you can publish more accurate information. So there are still a lot of things that people that you can examine to see, well, whether there are other interesting instantiation of this membership privacy notion that's applicable in particular situations. But that's sort of, I think that's topic for future research. And to be really honest, I think it's a topic that is really, really hard. So I'm sort of personally myself, I'm not sure how much more I'm going to drive towards this direction because I felt that whatever problem that I personally can solve sort of are mostly solved. So the problem that I really want to solve, but I haven't been able to solve after 7 or 8 years are sort of too hard for me to solve. So I think I'm out of time. And I'm happy to take questions offline, I guess.
Is there any short questions? Anything you want to differential question? Okay, thank you very much.